Welcome to our session on auto-instrumentation for GPU performance using eBPF. My name is Dominik. I'm a senior developer experience engineer for Grafana Labs. Now, oh, wait. Go ahead. Okay. Now, I don't work on these topics specifically. I usually work on making sure that whatever tools we put out there are actually usable by developers. But I'll still be hopefully getting some information across for you for this. My colleague here knows more about this topic.
Yeah, so my name is Marc Tuduri. I work as a staff software engineer in Grafana, specifically in the Bela squad. And yeah, as Dominik mentioned, we're gonna explain here one of the use cases of an experimental use case that we are developing in Bela. In this case is how to monitor GPU performance using eBPF.
All right, so as I explained before, I don't directly work with these topics, so I have the easy part of this presentation. I just have to convince you that there are issues out there, and it's not an easy thing to do. And then Marc has the hard part of actually telling you how we can solve those things. So for this first half of the sessions, I'll let you imagine you're Randy. So by day, Randy is a comedian. By night, other way around. By night, he's a comedian. By day, he has a VC-funded startup. And like every VC-funded startup, he's doing AI. So what do you need if you want to do AI? You need GPUs. You need lots of them. You buy video GPUs, A100, 200, whatever. He has a lot of money, so he buys a lot of GPUs. Now in this example, it's just 5 GPUs, but real companies have thousands of GPUs. And these need to be split somehow. Since we're not just using them for gaming, obviously, no one's just running Cyberpunk on them. They want to do some real work on them. Now that real work could be either model training or actually running live inference, so turning user input, computing trained models on them and getting the user some output. And you might have many teams working on many different projects, so you need to somehow assign this team gets to use this GPU for now, this other team gets to use this other GPU for now, and that somehow works. So this mystical scheduler could be Slurm, could be some Kubernetes operator. Teams get their GPUs, and everything is fine. Until it's no longer fine. And some GPUs start to die. Well, GPUs die, GPUs are a complex thing, things happen. Now, that happens relatively often, actually. If you're gaming, that might not be obvious to you because you're playing a game at 60 FPS, 120 FPS, and if there is one bit wrong, then maybe one of the pixels starts flickering weird, but you don't really notice it, really. But at large scale, things start to go wrong a lot of the time. Now this is some data from Meta from their Llama paper, and they were running their training session for over 50 days, and over these 50 days, they encountered around 500 failures. They counted them all up, and everything you see here marked in red, that's all GPU failure. And it doesn't have to be the same failure. It could be just the GPU doing something weird and the output is not right. But you notice there's a separate one for silent data corruption. So you run some function on a GPU, and you get some output, but the output is just wrong, and you have no way of verifying this. Then there's the classical just hardware issues. The GPU can just suddenly disappear from your host, and there's no real way around this. Overheating, thermal interface you see in there as well. So the average failure rate is around 1.6%. To remediate this, in the Meta case, they use cryptographic functions on the output, so you kind of hashed some well-known values and used hashing to make sure the data they expect is actually correct data. But ideally, we want to do some predictive maintenance and make sure we can observe what's going on in our GPUs. Now, to actually understand what's going on in a GPU, it's a bit more complex than when working with CPU data only. The rough data flow is you prepare some data in CPU space, you copy that data over to the GPU, you load a kernel into the GPU, so a kernel is like a small piece of code or a specific function to execute. This then gets executed, and you have to copy back the data from the GPU. And all of these steps can have failure points. You can copy the wrong data, you can get the wrong data back, the kernel might fail to execute. So yeah, it's not a simple topic. So one thing that might be obvious now as well is the CPU is actually responsible for making sure that stuff on the GPU runs correctly. Metrics we might be interested in is how many kernels did we actually launch? Does this correlate with the number we expected? Are there any data dependencies between these kernels? Like, is the output of one kernel relevant for the input of another kernel? Memory allocation, very interesting as well. Is the number of the amount of memory allocated the same amount of memory that was deallocated? Could be a failure case as well. And then there are some more advanced failure cases where async processing goes into factors into the entire data pipeline as well. You have to recalculate your dependencies. Things just can go wrong. So coming back to our friend Randy, he does what every great engineer does. He asks his favorite search engine, how do I monitor my GPU? And after a short session of despair, he comes back with, we're just going to set up hardware metrics. If the GPU starts misbehaving, there has to be some sensor in there to figure it out. And there are some projects that do exactly that. For example, the NVIDIA DCGM exporter, where DCGM stands for Data Center GPU Manager. It offers some basic metrics like GPU temperature, power usage, clock speeds, but that data doesn't really tell you what's going on inside of the GPU. You know that the GPU is doing something, but it won't really help you that much. Of course, if you have, on the previous slide you saw we have a scheduler in there, so the scheduler is taking care of when to launch jobs, where to launch jobs. So that has some metrics as well, so we can see, has the job succeeded or did it fail? But again, no detailed insight as to why this GPU is performing or behaving weird. The team at Azure built their HPC node health exporter, which builds upon the GPU metrics and actually communicates with the scheduler and says, oh, this GPU is showing some signs of weird behavior, we're just going to exclude it. So this prevents you from running code on faulty GPUs. But again, it doesn't really account for why there are failure states. Why do we reach these failure states? Is there something we can do different to avoid what's happening right now? So Randy searches some more, and he finds out profilers are a thing. GPU profiling. Useful stuff. You run your task with a profiler enabled, like Nsight or the PyTorch profiler, and you get some nice graphs. You can see, oh, there's memory, there's some memory operations happening here. We spent this much time doing this thing. You can see the data, how it flows through a bit. But again, this doesn't show you the whole picture. So you don't really get a large-scale overview, especially if you have many GPUs, many tasks going on at the same time. You run into the issue that you need to run this profiling command for every single execution of your code. Profiling has a huge overhead. It needs to integrate with the correct libraries. So if you're using some weird component that doesn't really support profiling, you're out of luck as well. And in our opinion, the biggest downside to the entire thing is profiling is the way it's currently done in the GPU world is a one-off thing. You encounter a weird behavior, you profile it, and then you have some results, maybe the bug is harder to reproduce, so it's not as easy to identify. And the output file is only local, so you get a profiling file at the end, you can inspect it, but it's hard to share it with your team. It's hard to, if you have 5,000 GPUs with 10,000 jobs, if you have a profiling file for every single one, you can't really correlate what's going on. You need to mix and match, okay, which job was this profile created, or which GPU was this profile created on, what's going on over there. Again, not ideal. Yeah, summing up, performance overhead. Sometimes you need to manually instrument profiling for it to work in the first place. You don't get CPU context as well. Like this whole structure of we first have to prepare the data, then copy it over to the GPU. You're losing out on that. And yeah, profiling is useful in some cases, but not generally the one-fits-all solution here. Now, Randy already lost enough money losing all of these GPUs, so he's replacing them with AMD GPUs now, instead of the NVIDIA ones. They're a bit cheaper, apparently. I don't know the current state of the GPU market, and by the time you're watching this recording, it might have changed again. So yeah, he replaces them, and now he has more problems, because most of these exporters are specific to a specific framework, library, framework, library, vendor, and he needs to go through the entire journey again, find new tools, figure out how this works with AMD. Basically, yeah, he's screwed. He can't do anything at this point. And now I have the fun part of handing over to Marc, and he'll tell us how we can fix this.
Thank you, Dominik, for the introduction. So yeah, let me introduce here Grafana Bela, which is our eBPF agent that we initially built in Grafana for instrumentation of Go applications, but we extended to somehow solve some of these issues or in experimental way. And yeah, some of the advantages of eBPF is that it's zero instrumentation. So that means that in the case of Bela, you deploy it in your server or where you have the workload of GPUs, and it's going to start to get insights automatically for you. You don't have to do like this long line of code that Dominik showed us, or like touching any of your code. It's also like framework agnostic. That means that doesn't matter if you are using PyTorch or whatever meta thing. It is capable to instrument all the CUDA operations or some of the CUDA operations for you. And since it's eBPF, it has a low overhead. It's fast, and it doesn't compromise any of the performance of your CUDA processes. So as I said, this is experimental, so if any of you are working on AI or GPU, please come back to us and say if that is helpful or how will you do. But yeah, so the first step that we did here is identify the important CUDA calls. There are many out there, but we select a subset to start experimenting with them. So we write some probes. An eBPF probe is like a little function that you write in the kernel, and it's going to be executed when a program calls that kernel function. In this case, it will be a CUDA function. And then we get data, and with this data, we can see what we can do with it. We had a process of getting all the CUDA libs and modules and do discovering. So we have to inspect what's there, and we have to take in consideration that there's also dynamic linking. And it's important to mention here that we can only we access to the CPU before and after the GPU calls. So we cannot, sadly, we cannot tap into the GPU itself, only the result of an operation. So there is no eBPF support for GPU, so all of what we're going to discuss now is at CPU level. So let's see an example how this works. So we have here a prompt that it goes to our favorite LLM system, and what this is going to do is going to process this data, and it's going to send it to the GPU via this CUDA launch kernel function, and the GPU is going to do the calculation, and it's going to return this calculation back to the LLM. Easy, no? And what Bela is doing in this case is just able to inspect at the CPU level again the execution of this CUDA launch kernel. And it's going to extract some data, and we're going to create a metric called GPU kernel launch kernel calls total, and that is going to be able to be scraped by Prometheus and later visualized in Grafana. Here's the definition of the probe for CUDA launch kernel, and as I said, this is going to intercept the launch kernel function in the GPU, and it's going to extract some metadata. The first arguments are passed via register, and from here what is interesting for us is that the func offset is going to be used later to infer the name of the kernel, and the remaining parameters are these grid and block coordinates. That is, this is going to be useful to obtain the cardinality of the kernel execution. Here, the cardinality is not Prometheus cardinality is is like the cardinality of the operation in the GPU. Yeah. So this is how we visualize the metric in Prometheus. So in here we can see that we are able to like fetch different CUDA operations, and of course there's going to be some that are more executed than others, so that's why they're higher on the value. And as you can see here, or well, maybe we cannot see, but since we executed this in a Kubernetes environment, we have by default Kubernetes metadata decorated. So we can see for each kernel operation in which pod and which namespace is being executed. And so this could be useful to, for example, to track which teams are using more or less CUDA operations in our company. Yeah, so here we have a Grafana dashboard, and in the top panels we can see the cardinality over time, and sorry, we can see the average cardinality, and on the bottom we can see how this cardinality grows over time. So with this, basically we can see like which kernel functions are doing more computation. Because roughly, like, the more cardinality is, they are using more GPU. And here in this second Grafana dashboard, sorry, I didn't mention here, this is like the execution of a prompt in a loop. So that's the metrics obtained over time. And in this case, we have a second prompt, and so we can see that there is a spike in the cardinality, because basically means that we are doing more operations. We have also this probe that is tracking the memory allocations of CUDA, but in this case it's not very useful because the memory allocation happens in Bootstrap. And we have this other probe that is more interesting because it tracks the memory copied from host to device and device to host, which is CPU to GPU and GPU to CPU. Yeah, and so here we have the visual representation of this graphic. Of this metric, sorry. Again, this is from the execution of that prompt. And as we can see, when there is like a second prompt, there's the memory allocation grows. And it's also interesting to see here that, of course, there is more memory copied from the GPU, from the CPU to the GPU than the other way around. This is basically because when we are sending a prompt, we are sending a large number of float numbers, and the GPU, it just responds with a few values, which is the answer to our prompt. And at the right side, we can see that the memory allocation, it also matches with the rate of CUDA kernel launches. So the more operations we launch, the more memory copies are we doing. In the probe of the CUDA launch kernel, we can also have this piece of code, which is capturing the stack trace of the CUDA kernel launch. And so we can extract this information, and we can unwind the frames using the symbols that we extracted from this function. And we can see something like that there are PyTorch kernels here and VLLM kernels. And we can visualize this with a flame graph viewer. But we have a problem because we are missing the rest of the stack. And this is because we are using frame pointers, and during compile time, the rest of the stack is gone because we did frame optimization. This is how we envision that we would like to see the whole profile. This is just with GDB and without the optimization, and hopefully with the open telemetry eBPF profiler utility that is out there, we can unwind the stack, and we can walk it and see everything without seeing only a few things. Yeah. So the limitations of our eBPF approach is that there is no information available on kernel execution time. That means that we cannot know how much takes one kernel execution, because most of the things run in parallel. So yeah. And the other things that other limitations, as I said before, we don't have access to the GPU hardware, so we cannot track things like temperature or memory utilization and all of this stuff. Yeah. So just to recap, the idea here is to close the gap between traditional GPU monitoring, as Dominik mentioned, and bring it to the modern monitoring solutions like Grafana and metrics. More architectures, maybe, but we don't want to instrument every LLM and every framework out there. We're just focusing on CUDA for here. We saw that there are some limitations to capture the context before and after GPU calls. And in the future, we would like to instrument more CUDA operations depending on which of those operations are more useful than others. And yeah, hopefully we would like to create a span with the HTTP trace that from the prompt and have all the information of the GPU call. But as we say, that's not so easy. So I think that's all. And yeah, so if you have any questions, please. Yeah.
So the question was if we have noticed any performance issues from using U-probes, because they are known to not be quite as fast.
I guess that you refer to performance degradation in the GPU, in the CUDA side, or?
No, on the CPU side, like when the U-probe is executed,
yeah.
it adds some overhead.
Yeah.
So clarification was it's on the CPU side when the U-probe is executed. When the U-probe is executed. In general, we don't have much performance degradation at application level, even with U-probes. Of course, like running K-probes for generic HTTP services is faster than U-probes, for example, for Go services. But
in this case, I don't have an answer for you because I didn't run the experiments or the benchmarks for in the GPU experiments. But as I can say, for the application side, the performance impact is very minimal.
So the question was, how much would the effort be to add more support for other GPU vendors like AMD or Intel?
Yeah, so the idea here, as Dominik mentioned, is that we just focus on CUDA. Maybe you probably know better than me, but maybe AMD also works with CUDA, or it works for a different framework. I don't think the effort would be much bigger because you have to do the same thing, which is every time that you wanna, either if it's like a protocol or a GPU framework, you always have to do something very hackery and go to the GDB and go to the symbols and inspect them, and it takes a lot of effort and yeah, like Hackerman looking at binary stuff, and I still struggle to do that, but yeah, you have to do the same thing for every new protocol or new framework that is out there. So it wouldn't be much effort, but for now we are just focusing on CUDA, and if we have validation of this use case, we can expand to other stuff.
So the question was if we have looked into using Sysdig for GPU and CPU profiling, if I got it correctly.
I don't know what's that. What's, can you?
I mean, Sysdig, it ends up using perf under the hood with kprobes, but it allows you to actually observe what's going on at the kernel level and system application level. Flame graphs,
So yeah, the clarification was that Sysdig allows you to have more comprehensive flame graphs of GPU applications as well. But yeah, I don't think we have looked that much into it, as we're currently just now getting started exploring that. We see the first customers asking for this, so we're only just getting started and yeah, looking at the CUDA perspective for now. All right, I don't think there are any more questions. If you have some questions, we'll still be around for a few minutes, I guess, as the conference is just wrapping up. There will probably be still some stickers left at the Grafana booth if you want to grab them. Yeah, thanks for attending our session.